So hi everyone, thanks. It's great to be here. So this is a little bit of a change in pace. We're going to talk about implementation detail. We're going to talk about some of the work that I've been doing at Ufora to make it easier to write scalable machine learning programs that can handle some of the kinds of algorithms that we're hearing about. I came to this problem because I wanted to understand why it is that when I work with bigger data sets, I have to write a completely different program than when I small data sets. And as a computer scientist and a programmer, I found that really frustrating. So I'll give you a simple example. So here is some Python code that can take a point and search a bunch of other points and tell you what's the nearest point, right? So this is actually a very basic part of, say, implementing something like k-means that Edo was talking about. Unfortunately, if you take that code and you run it in even a moderately sized data set, it's simply not fast enough to actually do anything. And if you were going to go rewrite it to be able to handle the kind of scale and volume that you're running into at a place like Google or Yahoo, it would look like a completely different program. And I guess what I'm trying to argue to you today is that that actually shouldn't be true. There's enough information in that source code to actually be able to tell how to generate an efficient implementation. It's just that we don't have something that can actually do that. And that's really what caused me to start working on my company Ufora and the platform that we developed called Pyfora. So Pyfora is a scalable implementation of Python. It basically takes regular Python code that's been written like it's going to run on a single thread and figures out how to make something as fast as if you've written a bunch of low-level C++ with API. So it's 100% open source, grass-fed code, so you can just go and grab it and do whatever you want with it. Check it out on GitHub. And I'm going to talk a little bit about sort of my motivation for doing this, the techniques that we're using inside of it, some problems versus other that we solve versus other kinds of platforms where you up by hand. So, practically speaking, our goals for the platform are to make it possible to write regular Python code. So you should actually have the same semantics in this platform as you would if you're writing normal code that you would run on your laptop. That's actually wildly untrue of most of these systems that people write. So if you produce an error in most distributed systems, it actually takes quite a bit of work to figure out where that error happened and why. Large-scale distributed systems have all kinds of race conditions in them. They can behave very differently depending on what happens to the hardware. We want all of that to go away. We want it to be really easy to actually use a large number of CPUs and GPUs without really thinking about it. And I think the most important point is that we want this to be able to happen without explicit intervention by the programmer. So we don't want people who are writing machine learning algorithms to actually be thinking, okay, I have to call this API, this library function to distribute the data. That should be an implementation detail. When you write code on a regular processor now, you don't think about, well, what is L2 cache on my CPU loading? You just run your code and it works. Why can't it be that way for distributed systems? So if you look at the way people scale things now, the most common thing is to actually code against an API. So the idea is you write your program and you go do the pseudocode like I showed you for K, and then you're like, okay, it works, it seems to do what I want it to do, and then you go rewrite the program to plug into some framework. And so this is a very manual process of altering the program code to make it work. But there's actually another way of doing this, which is to say, let's have a system that can actually analyze the semantics of the code and make that scale. And really, what you're saying is let's put the burden of making it scale back on the system. And this is actually something that's been done in a couple of contexts extremely successfully. And I would say probably, in my opinion, the best example of this working well is SQL, right? SQL has been around for decades, and you can now run programs that were written 30 years ago that are SQL queries on top of giant distributed Spark systems. And the semantics are exactly what they were 30 years ago, and we're able to take advantage of all of that new amazing infrastructure. The only problem is that SQL isn't terribly good for iterative machine learning. It's good for counting how many patient records you have, but not for actual modeling. I'd also point out that the things that people have been doing for programming on GPUs are so complicated that it's really not possible to do it with an API approach. You have to be able to think about it from a language perspective to actually make this work. So there are a lot of details in which one of these approaches you might pick. I won't go into all of this, but I guess what I will say is that broadly speaking, the point is that if you program with an API, you get a lot more control because it's a program and you're interfacing with it in a very explicit way. That control comes at the cost that you have to understand those details to make it all work. If you're going to do this with the language approach, you're not trusting the system to do all the work for you, which basically means the system has to be incredibly good for this to work. That's actually quite a big challenge, and it's one of the reasons why you've seen it take so long for these SQL on top of Hadoop, SQL on top of Spark implementations to catch up in terms of the performance and general purposeness of what they can do, but they are catching up because people have put a substantive amount of work into making that happen. And I guess my central thesis in everything that I'm doing is to say that if you do a good job with this, you should actually always be able to win with the language approach. So anything that you can write out in an API is some sort of structure, some sort of patterned way that you're interacting with your data, that if you wrote out, there's going to be an equivalent form in a language construct, and we can teach it to recognize that. But in the language context, you actually get a lot of benefits. You can actually read the code, you can understand what it's doing, and more importantly, the language implementation actually has a lot more information to work with than an API approach. So language implementation has all of your source code. It can actually reason about what you're doing and try and actually do deeper optimizations than are possible with an API-based approach. And that's really why I ended up wanting to do Ufora in the first place. So let's go back to our example. This code has actually 3 places inside of it where there's parallelism. You've got the function that computes whether or not 2 of your points are how far apart they are. You've got a function that says for 1 point, let's find the nearest point by looking at all of them, and then another function that says let's look at all the points, and for each one, compute that distance. There's actually 3 places in here where I could potentially do some kind of distribution. So if you said, okay, Braxton, go and take that code, you just started at Yahoo day 1, you go ahead and translate this into something fast, what would I do? I would go probably take that inner calculation, turn it into NumPy, and then go figure out basically how to distribute all the work. That's what I would do. And I would be doing the work that isn't actually that hard. I would just be following the road thing that I would do as a programmer. So my argument is that we can do this as human beings, but the answer, the way that we choose to do that, isn't necessarily going to be the same depending on the data that we have. So if you just handed me a couple hundred rows, it would actually be insane for me to try and distribute this. There was a great paper that came out a couple of years ago that pointed out that for actually a fairly large number of algorithms, if you're only talking about millions or hundreds of millions of points, distributing them in a Spark cluster is much slower than if you just have somebody write a clever C++ program that's very efficient, because there's overhead associated with distributing things. So maybe we don't want to distribute it, or more importantly, maybe we want to run this hundreds or thousands of times with different small slices of data. On the other hand, if I'm taking the classic case where I have points dimension is not that high, hundreds or thousands, and I have lots of points, the natural thing is to just distribute the points. Maybe you don't have that many centers, hundreds, thousands, tens of thousands, but it's smaller than the number of points. But just to throw it out there, imagine that your points were actually quite wide. So just to explain the iconography, the idea is that the blue boxes represent collections of points, horizontal white lines are individual points in your space. Imagine that you were dealing with images, and you had thousands of images, and you wanted to use this technique to cluster them. This is maybe something you might do. It might actually be more efficient to put slices of the images, the upper left corner on one box and the lower right corner on another box, and do those calculations in parallel and then join them. I don't want to really get into the specifics of whether that's a reasonable thing to do. I'm simply trying to point out that for that same code that you might write, depending on the kind of data that you have, you might actually end up with a completely different implementation, and you'd actually have to think about that. You might write completely different code. And as a result, you can't just have a one-size-fits-all. But my point is that there's enough information in the algorithm to actually be able to generate all 3 of those implementations if you only knew what the data actually looked like when you were writing it. And so I think this is the central thesis behind all of the language implementations. Say, let's defer as much of the selection about what we're going to do and how we're going to do it until we actually have the real data. Let's actually build something that can optimize itself based on experiencing running your algorithm on the data you've got, and then adjust the behavior accordingly. And if you can build something that actually does this, if you get it right, it provides some pretty enormous benefits. I think the largest one is that you as a programmer now have tooling and a framework that makes it much easier to say what you're actually trying to say. It means you can take a program and give it to someone else, and they don't have to understand all of these full-level implementation details. It actually allows you to use the language the way it was originally intended. So take Python. Python is an enormously flexible programming language. Like that source code I showed you, you can plug in anything for those row objects that kind of looks like a vector, images, NumPy arrays, lists, and it'll all just work. If you build a hard-coded implementation that works for a specific kind of object because you wanted it to be fast, then you end up losing that flexibility, which is, of course, the whole reason why we picked Python in the first place. So this kind of approach actually can solve a number of problems that people run into, practically speaking, using frameworks like MapReduce that I want to talk about really briefly. These are all things that we actually do successfully inside of the Pyfora implementation. So one problem that I hear people talking about quite frequently is this idea that the chunking in a MapReduce implementation is wrong, and then they end up either running out of memory and crashing and looking through logs to try and figure it out, or they end up with just a couple of jobs taking all of the time. And this is simply because you say to the system, okay, here's my data set, divide it into 1,000 pieces and put each one on a processor and go. And if you do that naively, it may turn out that the amount of time it takes to process each chunk isn't symmetric. Maybe a couple of those chunks have wildly more work to do than another chunk. And so people spend a lot of time tuning and trying to figure out how do I put the data into chunks. And if you get it wrong, you end up basically with a cluster of 1,000 computers operating at the speed of one. Not really what we had in mind. So the solution is to say, well, why can't we take that workload, run it for a while, and then when we see that some jobs finish, take the remaining jobs and split them in half and then rebalance the work. So this is actually something that we do in the implementation of Pyfora, and I'm not suggesting that you couldn't do this with an API. I guess what I'm really saying is that if you did do that with an API, you'd now have an API that was much more complicated because it would have to contemplate this idea that, oh, I'm handing you a chunk of work to your little mapper function, and you're gonna have to check periodically to see if you're supposed to split in half because there are other resources, and that's like work that's being placed back on the programmer. My argument is that's the kind of thing that compilers are actually very good at doing, is inserting checks like that into code and reasoning about how frequently they should be made, which is exactly what we do. Another problem I see people running into quite often is this idea of nested parallelism, right? So it's very easy to say, okay, here's an algorithm, I can kind of see where the parallelism is inside of each loop of the algorithm. But what if you have an outer loop around that whole thing that wants to run that algorithm in many different contexts? So you now have a much more complicated structure of how the individual tasks are relating to each other. Maybe that set of tasks is changing through time. You can do this with APIs. You can explicitly break it down, but it turns out that it's actually quite a bit of work for more complicated models. And oftentimes the actual explanation of what's going on is quite simple. So here's a little bit of source code that if you had the right objects plugged into this would work. That says, okay, I've got a function that fits a model by looping. Maybe inside of that there's some parallelism, and then I have an outer loop that says, let's run this over a bunch of different learning rates. So like boosting is a classic example where you might actually want to validate out of sample what your learning rate is. A language implementation can see all of this parallelism and actually exploit it. If you were to write that out by hand, it actually turns out to be a fairly large amount of code to orchestrate all of that. And I guess the final point that I wanted to touch on is something that I also see people struggling with, is this idea that sometimes breaking your problem down into something where each little task has a relatively small amount of memory isn't a trivial thing to do conceptually. You spend a lot of time trying to think about how to make that transformation. So a good example would be, imagine you have a bunch of sets of things. They're like all the customers that interacted with a given product, and you want to say, well, for all pairs of products, what's the common set of customers, right? Some calculation that needs to visit all pairs of sets. You might say to yourself, okay, well, I can do that as a MapReduce. I'll do a map on the individual set. But then the problem is that each job still needs to visit every single set, and if that whole set of things is very big, it's not going to work. And I've seen people do things like write all the data down to disk on every node ahead of time to try and solve that problem, and then loading it up, it ends up being this giant nightmare and it never works. But there is, in fact, a way to solve this kind of problem. And the way to think about it is to think about it as a cache locality problem, right? You have, if you have n things, you have roughly n squared over 2 sets of calculations, and you can group those calculations together in ways that use a common amount of information. And so, roughly speaking, it would look like this. Imagine that my grid extended, very far to the right and very far down. But I could look at that set of tasks and break it into blocks of tasks and say, oh, well, they all kind of use. I can do a lot of work with loading a reasonable amount of data. If you actually look at the way matrix multiplication routines are written, they actually think very much along these lines. My point is that you can actually infer this structure by, again, looking at the source code and detecting that this is what's going on and doing the scheduling in an appropriate way. So very briefly, I want to touch on some of the things that we actually do inside the implementation that make this work. I'm arguing that these techniques in general could be applied in lots of different places, but we've actually made a bunch of this stuff work very concretely. Probably the biggest thing that we did in our implementation is we said, let's not try and do all of Python. That's actually very big and very hard to reason about. Let's dial it down a little bit and say, once you make a list or a data structure, you can't change it. That constraint is actually incredibly helpful in a distributed context. It also lets us do a lot of optimizations on the compiler level that wouldn't be possible otherwise. We built a custom JIT compiler in order to do this that takes advantage of that. It also gives us, in implementation, the ability to take running code on one machine, understand what it's doing, pick it up and move it to another machine, checkpoint it. There's a lot of good things that happen when you fully control everything that's going on inside of the implementation. Spend a lot of time looking at what data individual threads are accessing so we can make those scheduling decisions that I had on the other page, so we can actually learn what that looks like and make those decisions. This is very briefly what it would actually look like to use the implementation. The idea is you import Pyfora, you have a connection to a grid, so think of it a little bit like using Spark, but directly from Python without having to code against MapReduce. You have a bunch of code outside of, that just describes some model that you want to run, and then the code that you want to run on the cluster, you put inside of this with block, and that says, don't run it, on my little tiny box, go and run it on the giant cluster and do all the work there, and then bring everything back. And the crucial point behind all of this is that anything happening inside of that with block, it's the same, you should get the same answer, exactly as what you would get if you ran it on your own machine locally. It should just be, way faster. Okay, so just very briefly, I want to talk about some of the things that we're actively working on in the project right now. We're always working on more library support. We've got coverage for the core constructs inside of NumPy and Pandas, because we want data frame code to just work unmodified. We're starting to look at some of the scikit-learn libraries, make sure that those are actually ported and will just sort of scale naturally. We're always doing more of that. One of the things I'm most excited about from a research perspective is we're actually spending time actually trying to learn from past examples how long individual functions are going to take and how much data they're going to read and how much data they're going to produce based on the actual values floating around inside of the program. If you can get this right, it can actually allow the scheduler not just to make reactive decisions to what's been going on in the past, but actually look forward into the future and say, oh, I can tell this function that you're running is going to allocate 100 gig of RAM. Maybe I'd better put it on a different machine ahead of time instead of doing it now, filling up and then realizing I want to move it around. So that's some pretty interesting stuff. I'm always working on more compiler optimizations, and then one of the things that we're most excited about is we have some prototypes where we can automatically compile down to GPU without you even really having to know that this is happening, and then figuring out how to do that and how to move both the data and the compute down to GPU when it's appropriate. So if I have my way, eventually when you're looking at an implementation of Tensor Flow, it'll just be a few hundred lines of Python that describe the neural network calculations and backpropagation, but all that data distribution and GPU work that they did that's so amazing will be just sort of implicitly handleable by the platform. So thank you, everybody. And if you have questions, please come talk to me. I love to talk about this stuff.